Tonight we're doing climate change. Climate change is a different topic than what we're going to be discussing a little bit later, global warming. A lot of times these are used interchangeably, but what we're going to do with global climate change, we're going to look at how the Earth's environment has changed over the years. We're going to go back hundreds of thousands of years, believe it or not. And then we'll look at the causes for climate change, all the way back to 800,000 years ago. And then we'll end on global warming this evening in terms of the lecture. What you're seeing before you right now is a tree. And what do you notice about that tree? Exactly. Nice, lush leaves here, and then basically bald, like you said there. Why is that? Is it just a diseased tree, or
leaning towards the light?
Leaning towards light, exactly. So there's a source of warmth there for that, and that's just a very small area that we're talking about. That's what we would call microclimate, a very small climate. Now, what we're going to talk about this evening is very large areas, global areas of climate change. And this is kind of interesting. You see some of the sources for these graphics here, but this talks about glaciation from 18,000 years ago. Now you're probably wondering, how do we know about what happened 18,000 years ago and how confident we are of that? Well, we'll get to that here in just a few minutes. But for now, just let's assume that we believe it. And what I'm tracing here is the southward extent of glaciation. And some of these areas obviously are still covered with glaciers. If you look down here in the bottom right, here is Iowa, and you see the glaciation that occurred 18,000 years ago. A portion of north central Iowa. That's one of the reasons why we have these nice, lush soils. The black gold that they call Iowa soil is because of the glaciation that moved south. And you notice a large part of, what is that, Illinois, almost all of Indiana and Ohio covered by glaciers. And so that was about 18,000 years ago. Obviously, they don't exist today. And this particular graphic shows how the glaciers retreated at different periods of our history. And up here at the top left, you see the glaciation that occurred. And then if we go 4,000 years into the future, you still notice that now some of the glaciers are retreating. We see portions of Wisconsin and portions of Minnesota now that are no longer, or at that time were no longer covered by glaciers, but still a nice little finger down into Iowa. And then by the time we hit 12,000 years ago, now the glaciers have retreated almost to the Canadian border. And then we get to 10,000 years ago, they've begun to retreat even further. The Great Lakes were caused by glaciers digging southward. And then we get to 8,000 years ago, and now the glaciers have completely retreated even further north than the southern provinces of Canada. Now, what's kind of interesting, and the thing that we'll look at tonight, we're going to look at a lot of graphs. But this graph down here has to do with temperature change about some average. You see we have 0 degrees here, +1, +2, +3 above average degrees Celsius. Where you see this 0, what scientists have done is they have taken an average period from 1961 to 1990, and they said that whatever temperature there is what we consider the average global temperature. And so they just took that period from 61 to 90. You could have taken another time period. You could have used 1900 to 2000 and set that as your average. But standard acceptable practice is that period from 1961 to 1990. So if we go back to 18,000 years ago, how far below that 1961 to 1990 average were we, or globally? Yeah, about 4 degrees Celsius. And you notice that as we move forward in time, from 18,000 to 16,000, we begin to see a slight increase, but not much, and then a slight decrease as we hit about 16,000. By the time we get to 14,000 years ago, the deviation from the average was about 2.5 degrees Celsius below the 1961 to 1990 period. And so at 14,000 years ago, we see that the ice or the glaciers have begun to retreat. And they've begun to retreat because of this warming. Now it's still quite a bit, 3 degrees Celsius below normal is still quite a sizable deviation from the norm. But we're moving in the right area. As we get up to 12,000 years ago, which is about right where I have the cursor at, as we went from 13,000 years ago to 12,000 years ago, what is the temperature doing in terms of the global climate? We go from about 13, this Bowling-Allerod period, down to 12,000. What are we seeing? Global what? Global cooling. However, you notice here the glaciers are still retreating. Because now at 12,000 years, we're only about a degree below the average. So while it's cooling, it's still quite a bit warmer than it was back 18,000 and 16,000 years ago. Now, going from this Bowling-Allerod period, and I'm going to spend some time on this particular graphic because we're going to see it several times. But going from there to the Younger Dryas period here, we have a distinct cooling. Kind of bottoms out about 3 degrees below the norm. And then all of a sudden, this sharp increase. Now, this increase went from about, looks like about 10,500 years ago up to 10,000 years ago. So in 500 years, in a 500-year period, which is a lot to us, but when you look at it in terms of thousands of years ago, that's a small increment of time. And so we go from -3 to almost normal. In 500 years, we increase the average temperature by 3 degrees Celsius. That is a rather rapid warming. And even if we didn't look at the numbers, what's incredible about this is that you can see the slope is very steep. Now, if you're looking for those types of steep slopes, where else would you identify these types of steep slopes? Dylan, can you identify one? A very steep slope similar to what we see here, coming out of the Younger Dryas period, which is a very cold period.
Right at 8,000 years ago? That's not past.
No. I see two.
What we're going through right now.
What we're going through right now. Boom. That looks pretty steep. I mean, put any numbers to it. Looks pretty steep. What else? Where else in history? What's that? Around, yeah. Yeah, it was just anywhere where you see that. Boom. So you have sharp spikes. What we're seeing now in terms of slope looks similar to what we've seen in the past, right? So right now you hear a lot of people talking about global warming and how things are changing pretty rapidly. Well, if we believe this data, it has happened before. You know, I'll get to the $64,000 question when we get to global warming. But then by the time we hit 10,000, 8,000, we were right around what our average temperature was 1961 to 1990. You had a little bit of dip about 8,000 years ago, and then you have this period called the Holocene maximum, where we're almost 1.5 degrees above normal. Now, during this period, which is about, about 5,000 years ago, we're about 1.5 degrees above the norm. Right now, according to this, we're only about 0.8 above the norm. So we have been warmer in the past. That has happened. In fact, when we go back 200,000, 400,000, 800,000 years ago, you're going to see even warmer temperatures. a reason for climate concern, global climate change. Everywhere you see on this particular map, where you see red is where flooding would take place. If you look at the peninsula of Florida there, it's completely in red, which if the polar ice caps melt by a certain percentage, Florida goes away. The area that I grew up in, down in southern Louisiana, 60 miles of coast, 60 miles inland from the coast, gone. You're at North Atlantic seaboard. Exactly. Places like New York and Washington, D.C. would be inundated with water. You can see up here in the northern regions here, there's quite a bit of flooding. Down here, looks like just north of Turkey, portions of Australia, Indonesia completely inundated, portions of between Taiwan and the mainland China underwater. So obviously, if you're living near the coast or within 60 miles of the coast, especially the Gulf Coast, you're concerned about this. Or, okay, maybe you're not concerned about this, but it should be somewhat of a concern. So, this is a particular graphic that's in your textbook. And what we're looking at here are sea surface temperatures for August 18,000 years ago. And current day, here on the right, sea surface temperatures. Now, do you see any differences in sea surface temperatures from 18,000 years ago versus current day, August?
25 is bigger, a lot wider now than it was previously.
So this 25 here, you're saying between this 25 and this 25?
The area is wider out in the Pacific, but also edging coming through southern and North America.
Okay.
It actually reaches all the way to Africa.
Before it curves.
Ah. So this 25-degree isotherm reaches all the way to Africa 18,000 years ago. What about the, look at the north-south placement of the isotherms. Especially look out over the eastern, or look over the Atlantic.
Wider, it's a lot wider area in the Atlantic, and in the northern and southern Atlantic, it's a lot wider now as opposed to 18,000.
Okay, so what you're saying here, and so the isotherms are a lot wider here compared to here.
And they actually go further north.
Exactly. So you've got this 10 degree, the sea surface temperature, 10 degrees Celsius, that is actually north of Great Britain, current days. But down here, 18,000 years ago, the 10 degree isotherm was quite a bit south of Great Britain. In other words, the sea surface temperatures up in this portion of the northern Atlantic were colder 18,000 years ago. So what would that say about winters over in this region of the world 18,000 years ago? A lot colder, exactly. And we'll learn why here in just a moment. What other difference? What about if you look at the southern hemisphere? Do you notice any major differences? What's that?
The colors on your PowerPoint.
Oh, yes, then compared to this?
I could just
If we look 18,000 years ago, the 10 degree isotherm seems to be about in the same location. Maybe it's a little bit further south current day. So it was a little bit colder in this region. So it looks like the poles were colder, so we went further north 18,000 years ago than currently today. Let me ask you this. Let's concentrate on current day here. What do you think the source of the warm water over here in the Atlantic? I mean, it moves it's all the way up into Great Britain to where it's almost 15 degrees Celsius. If we convert that to Fahrenheit, that would be, think about this a second, about 59, 60. It's pretty warm water up in that area. What do you think brings warm water up into the North Pacific, or North Atlantic? Any idea? We kind of talked about it a little bit when we were talking about El Nino, that chapter. We're talking about the different ocean currents. So, do you remember the ocean current that went from along Florida, along the eastern Atlantic, and up toward the North Atlantic? Gulf Stream. It's a ribbon of warm water that begins to move up. In fact, this is what we call the ocean conveyor belt, and there's a lot going on here. But basically what happens, and I'm going to start here over the northern Atlantic. I have it circled here. And you typically have pretty salty water. Salty water is more dense than water that's not as salty. So we're talking about salinity here. And so as the cold water from the North Atlantic, having a higher density because of a higher amount of salt, it begins to sink. And so this cold ribbon of water sinks and begins to move southward, just like I'm tracing it out. Now what happens if we begin to evacuate water from the surface? If we begin to pull water down below the surface and moving it southward, obviously we don't have, an island here. Where does the replacement water come from? Where I have the cursor. Well, let's say I'm pulling this Arctic water down south. So where would this water come from? Where would it fill in? Yeah, from the red current. That's a current that's coming up from the south. And it's red because it's coming from southern extremities down in the tropics. And so that water has been warmed by the sun, and it begins to move northward. Now, I'm going to go back to this cold current here. It begins to make its way down through south of Africa. It splits. Part of it goes up into the Indian Ocean and then begins to return in the direction that I'm showing here with the arrow, heading back to the north. Another part of that current begins to move out south of Australia and then begins to move northward into the Pacific, and then warm water begins to return. Now the whole idea behind this is that you've got warm water moving northward, and that warm water is carrying what in terms of water vapor? More water vapor or less water vapor than cold air? Cold water? More. Yeah, because you have more evaporation from warm water. So you're bringing in warm, moist water. It's warmer. You have more evaporation. You have more water vapor. So your chance of storms would begin to increase with this warm ribbon of water moving northward into Great Britain. Now what happens if you begin to shut this warm current of water off? What do you think happens to the temperatures in this part of the world, up near Great Britain? France, in that area. You shut the warm water off. It should get colder, right? How can you shut this current off? Well, I said it starts by cold, salty water, high salinity, begins to sink. The key is salty water. Salty water is more dense than fresh water. To get this circulation going, I've got to take water and I've got to sink it down below the surface and begin to move it south. So how would I stop this salty water from moving? Let's not look at temperature. I've got salty water. How would I get it less salty?
First osmosis.
Melt the ice.
Melt the ice, right? Ice up here is fresh water, right? If you melt it, it's a source of fresh water. And what they think happened, there's this thing called up here in Canada, the Gulf of Lawrence, or I'm not exactly sure. I can't recall what it's the actual name of it, but it's this region here of Canada where you began to have some ice that began to melt. And as that ice began to melt, it began to flow into this region. And so you have fresh water mixing with salt water. You're going to make the salt water less salty, less dense. And so now you're going to stop this movement of cold water from heading south. If you stop evacuating water out of this region, you're not going to be able to replace it with water from the south. Because what keeps this water from the south moving northward is the water being dragged underneath the surface and moved southward. So basically, when you have this melting occurring, you decrease the density of the salt water, which shuts down the circulation. That has happened many times in history, in geological history. That has happened. And when that has happened, that's shut off that warm, moist air, which led to colder, drier type of winters up in that region. Okay, so I've given you a little bit of background. Do me a favor, everybody. Would you shut your computers? Just plop them down. We'll just look up here on this. So right now I've given you some ideas of how temperatures have existed or occurred in the past. But at this point, all you have to go on is, hopefully I'm telling you the truth. Well, obviously, 18,000 years ago, we didn't have instruments. Probably didn't have people out back there taking those measurements. So what they did is they started looking for what they call proxy data. Data that they can look at in terms of tree rings. You've heard that before. Probably everyone in here has heard of looking at tree rings. One example of reconstructing past climates is they look at the growth patterns of these tree rings. And when you're looking at tree rings, you can't use all trees. You have to look at trees that undergo stress. And so the trees that you typically have up in the more polar regions, they don't see a lot of warmth. So you're looking at trees down in the mid-latitudes. And so what we're looking at is that these trees, each of these rings constitute a year. And during good years, where you have sufficient warmth, sufficient rains, the width of the tree ring from year to year is larger. And you begin to see some of the smaller ones here, which would indicate probably drought conditions that impacted the growth of this tree. So what they ended up doing is they began to look at these, and here you can look at it here. They're looking at it with an X-ray, and each of these lines indicate a growth. So this is 1950. If you look at 1950 versus 1951, which one had the better growth? 1950 or 1951? I can see it. So the width here 50 versus the width here 51. 50. So 1951 here, depending upon the tree, if it's impacted by droughty conditions, warmer temperatures, would indicate a change in climate. And so what they've done is they've taken trees across different regions of the world, and they come up with this graph. Here they used the zero line from 1881 to 1960 as the average temperature. So this is the average. And they started looking at tree ring data and came up with above and below average temperatures. And they found in 1450 that there was a deviation from the norm of about a half a degree Celsius. Back in 1600, almost 8/10 of a degree Celsius. And so what's really nice at looking at things like this is that we can infer periods of warmth and coolness. Now we don't know exactly the temperatures, but we can come up with a comparison against an average. We can also look at, you're a biology person. Anyone else in here a biology person? Anybody? Okay. So here we can actually look at corals and how corals are impacted. One of the things that they look at is they look at oxygen, O2, has a molecular weight of 16, regular oxygen. Well, on some occasions, you'll have this stray molecule of oxygen that actually has a molecular weight of 18. And so what they do is that they find that when you have more, I have to think about this a second, they look at the ratio of O18 to O16. Okay, just a simple fraction. And they find that typically, and I forgot what the number was, but like one molecule out of a million on average may have a molecular weight of 18. But times when this ratio begins to increase, in other words, you have more O18 molecules, then that typically means that that's a period of cooling. So as the ratio increases, in other words, as the top of the fraction, the numerator gets larger, then they say that that's affiliated with cooling. And so what you've looked at here is this particular graph here. A couple of things going on here. You have sea surface temperature anomalies up here, and then you have the delta of oxygen 16 anomaly. In other words, whether you had an increase, or actually the way you would read this is a decrease in O18, meaning you had more, your O16 denominator was larger. So if it was larger, they typically found that that was periods of warmth. So look at the, let's see, you had 0.5%, a half a percent increase or decrease in the ratio of O16. This is kind of weird how it's done. But if this increases, then the ratio begins to decrease, correct? You see that? Well, they didn't do it like that. All they did is that they looked at whether O16 increased in concentration or decreased in concentration. And so they found that periods where you had O16 increasing in concentration compared to O18, that corresponded to warming. And so, for instance, here, with about a half a percent increase in the molecular weight of oxygen that had 16, you had, it looks like, about a 3 degrees Celsius increase. Now, how they came up with that, I don't know. This is just the results of what they came up with. What you see coded in there in yellow are years of El Nino. We talked about warmth, increase in the warmth of the temperatures near Peru. And you notice that there's a pretty good correlation between years with El Nino and increases in temperature, but also increases in the amount of O16. If you look at periods where we had the ratio was smaller, then it was kind of mixed. You had some cooling, some warming, but not as pronounced a signal. Here, an increase in the O16. Here, an increase in temperature. In this particular period, and a decrease in temperature, a decrease in O16. So it's pretty cool that they can actually use biological processes to come up with temperatures, or at least how they vary from the norm. So we can look at tree rings, we can look at Lost my train of thought there. Help me out. What do we look? Coral. Looking at coral. We can also look at ice cores. You've probably heard about that. In this particular graphic here, is they've got basically what they do is they take a hollow drill and they drill down into the ice core. And the idea is that, like this particular graphic here shows, you begin to get snow, and this is the surface of the snow. And every year, especially in areas where you have a lack of melting, snow begins to build up. That happens down in the Antarctica and in the Arctic. And what's nice is that they can drill down into the snow and eventually into the ice, and they can see bubbles of air. You see all these little bubbles here? Those bubbles of air have nitrogen, they have oxygen, they have CO2, they have methane, all the gases that we have, water vapor, all of that. And they can look at these, they can analyze these, and tell if there is more methane or more CO2 for a particular depth. Now, if you have an increase in CO2, an increase in water vapor, an increase in methane, what would that correspond to in terms of temperature? Yeah, begin to increase it, because we know those are greenhouse gases. So there's a lot of ways they can go back and create these temperature graphs that we've been looking at. This is kind of an interesting graph. This is from the Antarctic, and notice this one goes back, looks like 450,000 years ago, and it looks like CO2 in parts per million by volume. The blue corresponds to the temperature, change in temperature, which is over here on the right-hand side, and then the red corresponds to the amount of CO2, so they were able to drill down, look at the CO2 at different times throughout the past, and it's kind of interesting. You see as CO2, we'll start here at about 450,000 years ago, CO2 begins to decrease. We also notice that temperature begins to decrease. CO2 begins to increase, temperature begins to increase. Now notice, I'm using CO2 increasing or decreasing, and then temperature increasing or decreasing. Now some will say the temperature decreases or increases naturally, which causes CO2 to increase or decrease. Let me ask you this. Let's say, for instance, that, let's just subscribe to the theory that that CO2 doesn't cause warming. The warming causes an increase in the concentration of CO2. So what happens if we begin to melt Antarctica? And we continue to melt it, and we melt it, and we melt it. And eventually we expose what? Land, leaves, dead animals. Those are all made up of carbon. It's a source of CO2. And so you begin to load up CO2. Well, let's say you begin to cool again and you replace it with ice. That decreases the amount of CO2. So the big argument here is the temperature change being caused by CO2, or is CO2 changing because temperature is increasing or decreasing naturally? That's what they're struggling with. Okay, climate through the ages. We've seen this particular graph, and some of the things that I have listed down here are some sources for coming up with temperatures. And we've talked about a couple of these: ice cores, tree rings, corals. There's a lot of ways that we can reconstruct past climate. This particular graphic I think is kind of interesting. This top one is how global temperature has changed from 1860 to 2000. The reference, the 0.0, I suspect, I'm not positive, is probably, looks like it would be the 1961 to 1990 years. That's a common one. So from 1860 on up to about 1935 or so, we were below average in terms of temperatures. And then from the 1940s, now keep in mind, this is global. This is globally. We stayed right around the zero line, and then from 1980 on, about 0.3 degrees above normal. So about 0.4 from 1860 up to about 0.3 so about 0.7, 0.6 change in temperature as we came from the 1860s. Now, if you look at northern hemisphere, for that period from about 1860, see this is 1850, so where I have the cursor, we see that from about 1850 to about 1900, the temperature was level. So it was below normal, but it didn't change very much like the global temperatures we see here. And then it looks like, let's see, this is 1850, 1900, 1950. Looks like about 1925 or 1930, we saw a sharp increase in the northern hemisphere. And this, globally, from about 1925 to 1930, we saw a more gentle increase. So from that period, 1925 to about 1935, the northern hemisphere had a significant increase in temperature, whereas globally, not as significant. So that means the changes that were going on in that time period were mainly confined to the northern hemisphere. Any idea why? Let me just show you a picture of the northern hemisphere and southern hemisphere. Any idea why you might see a greater temperature change? This goes back to chapter 2, the experiment on soils, the wet soil, the moist soil. What's the difference between the northern hemisphere and the southern hemisphere?
More land.
More land in the northern hemisphere. We talked about with water, has a higher heat capacity, so it takes a lot more energy to change the temperature, whereas with land it doesn't take much. And so the fact that we just have more land in the northern hemisphere can have an effect on our temperatures. These are all natural occurrences or changes in temperature. So, some possible climate changes. We're going to take a break here. It's 7:25. We'll meet back here about 7:40, and we'll talk about some of the possible changes of global climate. So. Brandon, you were kind of rocking back and forth there a couple of
I didn't sleep very well last night, so.
Thought we were going to lose you there, man. I think you probably need a few more hours than that. Okay, so we've talked about basically temperatures throughout history, how they've changed. We've seen there's been a natural up and down oscillation to temperatures, but what we'll look at in the next few slides is we'll find out factors that actually cause climate change. And some of you may be familiar with this. There are basically what we put up into the atmosphere from volcanoes, and right now that volcano in Iceland is kicking up a lot of sulfur. We'll learn a little bit about what sulfur dioxide can do once it gets into the atmosphere in terms of affecting temperatures. It also puts out CO2, nitrogen. It puts out a lot of gases into the atmosphere, water vapor. We'll also look at the different orbital orientations of the Earth. You all have heard that the tilt of the Earth is 23.5 from true, off to the side. That actually changes. That varies anywhere from about 22 degrees on the tilt all the way to 24.5, which is more of a tilt than the 23.5 that we currently have. Also, the shape of the orbit, we'll look at that, and then how the continents have moved over the years, over the many millions of years. We'll talk a little bit. All of these have an impact on global climate change. So we'll look at the first one. This has to do with, and I don't know how many years this was ago, millions of years ago, but you notice you can make out North America here, South America here. South America was connected to the continent of Africa. Europe was connected to the North American continent. You notice there's really no space there for the Atlantic. And so originally, portions of Africa, especially, see if I can get the cursor up here, Africa was down near the South Pole, at least the southern portion of Africa, right along the tip. South America, the tip there was sitting right near the South Pole. And what's kind of interesting with this particular graphic, it's shown how the continental plates begin to drift with time. And so you see Africa here. Give me just a moment. On my cursor. You see Africa is shifting in this direction, or did shift in that direction. This part of Africa shifted northwestward. The North American continent began to shift north and westward. What's kind of interesting is that portions of, and I'll just use Africa as an example, they have found fossils where they have found tundra type of vegetation that's only associated with cold regions in Africa. And the only way that they can explain this is with this theory of plate shifting, continental drift. So portions of Africa in the geological past have been very cold, being near the poles. And then you see current day, we're still drifting. In fact, the North American part of the continent is drifting off to the southwest and to the west. South American continent is drifting off to the north and west. The whole idea behind this is that climate change can be a function of the shifting continents. And so where we've seen really cold temperatures before, warm temperatures, is in part due to the shifting of the continental plates. Another one is by what we call outgassing. In this particular picture, you see a volcano releasing what I've shown here is nitrogen, carbon dioxide, water vapor, and sulfur dioxide. We'll talk a little bit how that impacts things at this point. Now, if you have a volcanic eruption and it's spewing out CO2 and water vapor, what impact would that have on the climate? Yeah, we go back to greenhouse gases. That's exactly right. You have excess CO2, excess water vapor is probably the most efficient greenhouse gas. SO2 does kind of an interesting thing, sulfur dioxide. It sits up there and it actually reflects a lot of the incoming shortwave radiation from the sun. And so sulfur dioxide, if it's reflecting a lot of shortwave radiation coming in from the sun, what would that do for surface temperatures? What's that? Surface temperatures. So if sulfur dioxide is sitting up there reflecting a lot of incoming shortwave radiation from the sun,
Reflecting it back into space. Or
yeah,
that's what's like cool. It's going to cool off.
should be a net cooling. In fact, what they found is with SO2, during the day there's a net effect of cooling, but at night there's a net effect of heating, because that CO2 is also emitting long-wave radiation down to the surface of the Earth. But for the most part, it's a net cooling effect. And I don't know if this might be a picture of Mount Pinatubo, which erupted in 1991. What ended up happening, and I've got a couple of graphs in here, but it significantly impacted parts of the globe in terms of summer temperatures. I was in Kansas at the time back in 1992 and 1993, and we were some 3 degrees below normal over portions of the Midwest. A large part of that was due to all the debris that was spewed from Mount Pinatubo. It was a huge eruption, and I'll talk a little bit about it. Even right. What's that?
Where is it?
That's Mount Pinatubo is in Philippines. Yep. Yes, I should point that out. Yep. So it's sitting down there in the Philippines, the Western Pacific, or I guess it'd be the Southern Pacific, actually the Western Pacific. And what happened there had an impact thousands of miles away. That's a good point. because we know that global winds typically go from west to east, so all the ash and soot, all the gases were moved from west to east. This is kind of a busy graph, but it actually, let me see if I can spend just a moment. It shows the different eruptions and the deviation from the normal in terms of temperature. Krakatoa, which I would assume would be a Japanese. Does anyone know Krakatoa? I could be wrong, but Krakatoa erupted in 1883. And the way you look at this is that you notice I'm pointing to the 0 down here at the bottom of the chart. That is the point of eruption, and then it goes in months, in other words, before the eruption. So we're looking at, looks like 5 years before the eruption. And then we go out into the future after the eruption, which is really what we're interested in, because we want to see how temperatures are impacted. So there's a lot here. Let me just go to Pinatubo. The months leading up to the eruption, a year before the eruption, the average temperature, global temperatures were about 0.4 of a degree above normal. Back in, let's see, Pinatubo erupted in 91, so this would have been back in 1990. And then the eruption occurred, and you don't really see a big difference in temperatures right before the eruption and right after the eruption. You see where I'm showing this at? They're both right around 0.2 above. But then look what happened a year and even 18 months later. It dropped almost 0.5 degrees Celsius because of a single eruption that occurred a year to 18 months before that. That's a very dramatic one. You see some other ones up here. Here's one, Pele, Soufri, and Santa Maria in 1902. At the point of eruption, you saw that as we went out 12 months, 24, 36, 3 years after that eruption, it was 0.5 degree below normal. Now, what I think is really interesting is in this particular graphic, they take the Krakatoa, the Pele, the Agong, the El Shakan, they combined all of those together, and they came up with a composite one. So they added all of these together, and if you look at it, yes, exactly.
There's a mountain composite.
And they've done a composite, which really will bear the point I'm trying to make here, is that before an eruption, you have some above normal, some below, but after the eruption, 12 months, 24 months, even out to 36 months, the net effect is cooling. So a lot of that is the sulfur dioxide. Now what's interesting is you're kicking out a lot of CO2, a lot of water vapor, and what will end up happening is nighttime temperatures will be warmer than normal. Because recall, the Earth is constantly radiating infrared energy, that excess CO2, H2O, any greenhouse gas will absorb it and radiate it back to the surface. But in terms of daytime temperatures, the net effect is cooling because the sulfur dioxide reflects a lot of that incoming shortwave radiation. So that's yet another impact of global climate, is what we're seeing in Iceland. It'll be kind of interesting. I was watching the news yesterday, and they were talking about there's another volcano up there in Iceland that when this particular volcano, the one that's currently having some activity, when it begins to rumble and spew out some gas, the larger volcano, which is not far away, tends to have these massive eruptions. They have in the past. They're not saying it's going to happen, but it has happened in the past. And you get a huge eruption. It would be kind of, hopefully it doesn't happen because, then there's a lot of bad impacts. But if it does happen, it should be interesting to see if it would have an effect on our climate. This particular graphic right here, you see here right along the equatorial region, this is the output. It says here 20 million tons of ejected sulfur dioxide. And I don't know how they measured that, but they come up with an estimate of 20 million tons of SO2 had actually been ejected from Pinatubo and got caught in the westerly winds, and you see it's global. It's made its way around. And you see what happened here in terms of temperature changes. Pinatubo erupted in 91, and then we had temperatures decreasing, average temperatures decreasing, all the way to 1990, almost 1993. So these types of volcanic activity can have an impact. I mentioned here the greenhouse gases like CO2, water vapor, all of those will tend to keep higher temperatures at night, have those occurring. This particular graphic here is kind of interesting because it takes a look at carbon dioxide fluctuations. And I've already showed you this from earlier, but it goes back to 400,000 years ago, and this is that same graphic. They took that ice core down in Antarctica, and whether it's the increase in temperature that increases the rotting vegetation, which increases the CO2, or whether it's the CO2, the increase in CO2, which is causing the increase in temperature, it's debatable, but you can see there's a strong relationship here between the two. Now, one thing I want to point out, right here at the present time, it's showing our, let's see, present time carbon dioxide, about 300 parts per million by volume. That's actually, it's higher than that, but this is obviously a little bit older graph. Temperatures in red. And so we're showing temperature here in our recent history, maybe a decade ago. We have an increase of, let's see, 3, 2, looks like about 1 degree from the normal. Do you see that? This is the temperature relative to present climate. So we're right about 1 degree above normal. Is that the warmest that you see? No. You look back here, let's see, these are 25, 50, at about 125,000 years ago, we had almost a 3.5 degree increase. And if we go another, let's see, 125,000 years ago to almost 250,000 years ago, so another 100,000 years later, we had a peak. And another 100,000 years later, we have another peak. And it looks like another 100,000. So there seems to be this 100,000 oscillation of temperature. So between every 100,000 years, we have a peak. And it looks like from here to about here, about 125,000, we have cooling. So there's this period that we go from very warm to very cold or cooler, below normal. This is almost 8 degrees below normal here. I'm looking at this particular point where the cursor's at. So 8 degrees below what our current climate is to almost 4 degrees above. And that time period, let's see, if we're 125 here, there's about a 25,000 year difference there between these. And a lot of these are pretty similar. But this 100,000 tends to stand out. I mean, I can see that pretty easily. Well, that corresponds to something. And kind of keep that 100,000 year period in the back of your mind. Now, this is a really interesting slide. This is one of the most interesting slides because I came across this the other day, and I had not seen this one before. But this is the ratio of carbon dioxide. This R is the ratio of carbon dioxide from the, let's see, how did this go? The ratio from current CO2 levels compared to past. So if we have a ratio, again, we're dealing with a fraction, right? So if we take CO2 and we compare it to CO2 presently, okay, so we've got a CO2 presently, whatever that's, like 350 parts per million by volume, and we look at CO2 in the past, and this is the ratio of CO2 How do we get this number to increase?
The lower number needs to be smaller.
Okay,
Or
so that's one way. But let's just assume, and I didn't mention this. Let's just keep this the same. So what would we have to do to this number? Increase it or decrease it? Increase it. So this particular graph looks at the ratio of carbon dioxide in terms of CO2 in the past compared to some value in the present. Check this out. The value, well, let's look at present. We're right down here, bottom right-hand corner, and it looks like we're at about a ratio of about 2. Do you see that? Going right across. We're talking about global, talking about the amount of CO2. What about up here? The ratio, and this is about 450 million years ago, the ratio is about 22. The amount of carbon dioxide, if we go from 2 to 22, is what? How big of a jump is that? Or 11. Right. So if we start 2 here to 22 here, at one point, 450 million years ago, according to this graph, we had 11 times more CO2 in our atmosphere than today. That's a lot. And then you have down here, so here extremely high, begins to decrease, kind of stays the same for a few million years, 100 million years. It just sounds funny. Then we begin to decrease to the present day values, which is what we're measuring it by. So this is interesting. CO2 has been a lot higher, 11 times higher in the past. Okay. So there's one last way that we can look at climate change. One way was the movement of continents, where they were located at one time and they drifted. The other was volcanic eruptions changing the content of the atmosphere. This last one has to do with something called the Milankovitch theory. And it was a gentleman, I think, back in the 1880s who started looking at the different parts of how the Earth orbited, or how the Earth orbits. One way that you can look at is at times our orbit around the sun is more circular, as shown by the solid line, compared to sometimes when it has a higher eccentricity. In other words, when it's more oblong. What's that?
During a leap year, it's more oblong.
No, actually, these goes, as we're going to learn here, these change every 100,000 years. That's where I told about the 100,000. What's kind of interesting about it, to go from this circular orientation, which is where we're at now, to more of an eccentric type of orbit is 50,000 years, and then back from a more eccentric type of orbit to a more circular orbit is another 50,000 years. So we're talking about 100,000 years to go from circular back to circular to more an eccentric. Well, the more I say this, the more eccentric orbit back to a more circular orbit. There's that period. It's kind of interesting. So the way the path of our orbit around the sun changes seems to show up. See if I have it here. Seems to show up in the ice core. So from here to here, 100,000 years. Here to here, roughly 100,000. But if you go from here to here, halfway through, that's about 50,000. So let me ask you this. Circular, what would you have? Would you have a circular orbit here or a more oblong orbit? What would you guess? You got a 50-50 shot. Pick one. Okay, so if we go oblong and then we go about 50,000 years, we go from oblong to more circular, and then from a more circular, from 50,000 to 100,000, back to oblong. So what do you notice about this particular It's closer to the sun with circular path. More oblong this way. So which one would you think would produce a warmer temperature? More circular. You're going to be closer, right? Let me see. I'm asking. Okay, this is something that we talked about. I don't know if we talked about this in chapter 2 because I didn't really go into seasons so much. But in January, we're actually closer to the sun. It's a very small. It's only about a 3 or 4% difference in distance. But in January, we're closer to the sun than we are in July. So July, we're further away from the sun than we are in January. So what ends up happening if you go from this circular orbit? So let me see if I want to make sure I make this very clear. So in January, when we are closer to the sun currently, and then we head to July, we're moving further away from the sun. You with me? So let's say we move to this more oblong orbit. Now at this point, if I can say this, so at this point, God bless you. So at this point, when we move more toward the oblong orbit, at that point, let's see, how do